Hi, today we're talking on Viva Bites about allometry. So what is allometry? Allometry, there are different definitions. So the first one we can posit is that allometry is the study of the relationship of body size to shape. Another definition is allometry is variation in various traits that is explained by or associated with variation in size. So in essence, there's some relationship with size and shape. So allometric scaling is any change that deviates from isometry. When was the concept of allometry discovered? So the concept was discovered when people plotted pairwise log transform length measurements of organisms and found that these pairwise plots fit remarkably well to straight lines. And so you can get constant ratios between the relative growth rates of different parts, which accounts for this straight line. There are different types of allometry. So ontogenetic allometry is the shape variation with growth, so throughout different stages of life. Static allometry is the shape variation among individuals of a given age, and if there's any dimorphism in the species within the same sex. You've got interspecific or evolutionary allometry, so this is a comparison of species. Fluctuating asymmetry of shape may have a component of allometry where asymmetry of shape is an allometric consequence of asymmetry in size. You can also have allometry caused by genetic factors and also by environmental factors. To be able to disentangle them, you really need to think very carefully about the study design. Coming on to bivariate and multivariate generalization, so we'll start with bivariate first. Technically, it's not strictly a contrast because bivariate allometry is actually a special, simple case of multivariate allometry. In biology, a practical application is to measure how, for example, a small change in the overall body size leads to an enormous and disproportionate increase in the dimensions of an appendage. Usually one trait is considered as the trait of interest and is plotted on the vertical axis, whilst the other trait is considered as a measure of size and is plotted on the horizontal axis. So for example, centroid size is often used. The slopes in pairwise plots of log transform measurements indicate the ratios between the relative growth rates of the respective traits and are the basis for the terminology of allometry. The relationship between two measured quantities is often expressed as a power law equation, so y equals kx to the power of a, or in logarithmic form, log y equals a times log x plus log k, and a is called the scaling exponent. We're now looking at a specific case, isometric scaling. So if both traits have the same relative growth rates, the slope in plots of log transform traits is 1, and the dimensions of both traits are the same. So their proportions do not change as size increases, and this is called isometry. So a perfectly isometrically scaled organism would see a volume-based property change proportionally to the body mass, so the slope would be 1. All surface area based properties changed with mass to the power of 2/3, because surface is squared length and mass is cubed length. So 1 over the other is 2/3. And all length based properties change with mass to the power of 1/3 for the same reason. An example is in frogs. So aside from metamorphosis, frogs grow isometrically. So if the legs are as long as its body and the frog increases in size, then the legs will remain proportional. Isometric scaling is often used as a null hypothesis in scaling studies, with deviations from isometry considered as evidence of physiological factors forcing allometric growth. Isometric scaling is governed by the square-cube law. So an organism which doubles in length isometrically will find that the surface area available to it will increase fourfold, whilst its volume and mass will increase by a factor of 8. But why does allometry exist? Well, isometry can be an issue by creating mismatches. For example, if the long surface was multiplied by 4, but the volume of tissue it must support is now 8 times the original size. Second example, if the mass is multiplied by 8, but the strength of the bones and the muscles, which incidentally depend on the cross-sectional area, is only multiplied by 4, then you're not going to have enough strength to carry that mass. So a solution to this is changing proportions during growth, and this is called allometry. You can have negative and positive allometry. So negative is when the values are smaller than predicted by isometry. For example, a volume-based property was found to scale to mass to the 0.9 power instead of 1. And in the case of positive allometry, when values are larger than predicted than isometry. So, for example, if a surface area based property scales to mass to the power of 0.8 instead of the 2/3 or 0.666 power. So an example of positive allometry is when limbs are relatively longer in a larger bodied species of monitor lizards. How do you determine if a system is scaling with allometry or isometry? Well, first, you need to determine the expected relationship to compare the data to. So you can use dimensional analysis for this. So for example, let's say that mass scales with a slope of 5 in relation to length. That doesn't have much meaning unless you know that the isometric slope is 3. So in this case, the mass is increasing extremely fast. So step 1 was to determine the expected relationship. Step 2 is log transforming the data and get a linear regression. In the third step, comparisons can then be done using the least squares regression with a 95% confidence interval or reduced major axis analysis. Sometimes the two analyses can yield different results, but they often don't. If the expected slope is outside of the confidence interval, then allometry is present. Let's come on to multivariate generalization of allometry. If there are more than 2 traits, then you need to be using a multidimensional space where each log transform measurement corresponds to one axis. Each bivariate allometric plot is then a projection from this multidimensional space onto the plane defined by the axes that correspond to the 2 measurements, whilst the multivariate generalization of these straight lines in bivariate allometric plots is a straight line in the space of log transformed measurements. To estimate this line in the multivariate space, Jolicoeur, 1963, suggested to log transform the measurements, do a principal component analysis on the covariance matrix, and then use the resulting principal 1 components as the estimate of the allometric line. As PC1 accounts for the most variance, the sum of the variances in all the directions perpendicular to it is then minimal. Just as a reminder, Jolicoeur is part of one of 2 schools of thought in terms of dealing with size in the case of allometry, and the Huxley-Jolicoeur school of thought doesn't distinguish size and shape, so PC1 will include size. So just coming back to using PC1, the coefficients of the PC1 indicate the direction in the multidimensional space, and the PC1 coefficient of each variable can be interpreted as the cosine between the coordinate axes for that variable and the PC1 axis. The bivariate allometric coefficients for specific pairs of variables can be obtained from the ratios of the respective PC1 coefficients. Why use a log-log transformation? Well, there are two reasons, a biological one and a statistical one. So let's start with biological one. So log transforming puts the numbers into a geometric domain that is so that proportional deviations are represented consistently, independent of the scale in units of measurement. In biology, this is appropriate because many biological phenomena, so growth, reproduction, metabolism, and sensation, are fundamentally multiplicative. And statistically, it's beneficial to transform both axes, then perform the linear regression, as this will normalize the data set and make it easier to analyze trends using the slopes of the lines. Before analyzing, it's really important to have a predicted slope to be able to compare this analysis to.